Hello everyone and welcome to Control Engineering and Control Theory tutorials. In this tutorial we explain how to use the final value theorem to compute a steady state error of a control system. What is the importance of this problem? Well, often in practice you will encounter a problem of computing the steady state error of a controller, and consequently you will have to use the final value theorem to solve this problem. So let's learn how to tackle this problem. Here's the problem that we want to solve. Given a transfer function that looks like this and a unit step reference signal, this is a very important information, we want to compute a steady state error for tracking this reference signal. Let's learn how to solve this problem. To solve this problem, first we need to recall the basic definition of the transfer function and what is the physical meaning of the transfer function. The transfer function relates the output of the system, denoted by capital Y of S in the complex domain, with the input to the system in the complex domain. So we have this formula. Y of S is W of S multiplying U of S. Over here, Y of S is the Laplace transform of the time domain output, Y of t. This is how we denote the Laplace transform. Similarly, U of S is the Laplace transform of U of t. Y of S is the output, and U of S is the input, or in our case, reference signal. W of S represents the complete closed-loop transfer function in our case. And our goal is to compute the steady-state value of the error. In the time domain, the error is defined as E of t is reference signal R of t minus the output of the system. Again, over here, R of t is simply U of t in our case. Now, if we apply the Laplace transform to this equation, we will obtain Laplace transform of E of t is equal to, let me just nicely write this, is equal to a Laplace transform of R of t minus Laplace transform of Y of t. Okay, we will denote the Laplace transform of E of t simply as capital E of S. And let's write it over here. So E of S is the Laplace transform of the error signal. And this is the error. Similarly, the Laplace transform of R of t will be denoted by capital R of S. So we'll have that capital R of S is the Laplace transform of time domain signal R of t. This is our reference. So we have E of S is R of S minus Laplace transform of Y of t, that's Y of S. Over here, instead of R of S, we can simply write U of S. And by using this relationship, we will have U of S minus, what do we have over here? Instead of Y of S, we can write W of S multiplying U of S. And consequently, over here, we will have U of S multiplying, let's see, what do we have inside of parentheses. Inside of the parentheses, we will have 1 minus W of s. And note that we can write this expression like this mainly because the system is single input, single output. A more correct version of this equation is actually to write it like this: 1 minus W of s multiplying U of s. However, since all the variables are scalars, both versions are correct. However, if W of s is a matrix, here you will have the identity matrix minus W of s matrix. Now, in our case, U of t is a unit step signal. In the time domain, this signal is written as 1 multiplying h of t, where h of t is a Heaviside function, or the Heaviside unit step function. If we apply the Laplace transform to this equation, we will obtain U of s is simply 1 over s. Now, by substituting this expression in this general formula for E of s, we will obtain that E of s is 1 minus W of s multiplying 1 over s. Okay, so here's the derived expression for E of s. We want to compute E at a steady state. That is, we want to compute E at infinity, that people sometimes in the control theory denote by ESS. ESS, standing for steady state, is the limit value when time goes to infinity, E of t. However, what's the issue over here? We don't have the time domain version of capital E of s. One approach would be to substitute Ws over here, then to compute the inverse Laplace transform, and to do that we will have to do partial fraction expansion, and we will probably need 20-30 minutes to solve this example. However, there is a shorter and more elegant way to solve this problem. And the idea is to use the final, I will write it here, final value theorem. Very important result in control theory. Let's briefly summarize the final value theorem. Here is the statement of the final value theorem. If all poles of capital E of s are in the open left half of the complex plane and at most one pole is at 0, then limit value when t goes to infinity of the time domain signal E of t is the limit value when s goes to 0, s multiplying E of s. So here's the main idea. We look and analyze capital E of s and we compute the poles. If all the poles are stable, we can apply the final value theorem. Also, if there is only a single pole at 0 and all other poles are stable, then we can also apply the final value theorem. And the final value theorem will tell you that the steady state value of the control error is actually simply computed as the limit value when s goes to 0 of s multiplying capital E of s. That is, we can simply compute the steady state value without actually going back to the time domain. So let's apply the final value theorem to this problem. Okay, so first of all, let's see what are the poles of E of s. To do that, let's transform E of s. E of s is equal to 1 minus, and let's substitute W of s. The W of s is s plus 5 divided by s squared plus 3s plus 2 multiplying 1 over s. Furthermore, we will have that E of s is equal to, let's arrange everything over here. In the denominator, we will have s squared plus 3s plus 2. Everything should be multiplied by s, and in the numerator, we will have s squared plus 3s plus 2 minus s minus 5. Okay, so E of s finally becomes, in the numerator we have s squared plus 3s plus 2 multiplying s. Actually, in the denominator we have this, and in the numerator we have s squared. And let's see, 3s minus s becomes plus 2s. And over here we will have 2 minus 5 is actually minus 3. Okay, now, so what are the poles of E of s? The poles of E of s are the zeros of the polynomial in the denominator. In the denominator we have s multiplying s squared plus 3s plus 2, and this is equal to 0. 1 0 is obviously at 0, and we have 2 additional zeros. These zeros are found as zeros of this polynomial, and they are. To compute these zeros, we simply need to apply the quadratic formula. So we have minus 3 plus minus square root of 9 minus 8 divided by 2. Consequently, s2, 3 are actually minus 3 plus minus 1 divided by 2. So we have that s2 is minus 3 minus 1, that's minus 4 divided by 2, that's minus 2, and s4 is actually minus 3 plus 1 is minus 2 divided by 2, that's minus 1. We can see that these two poles are strictly in the left half of the complex plane, and we have an additional pole at 0, and this is a pole of multiplicity 1. That is, this is only a single pole at 0, and consequently the conditions for applying the final value theorem are satisfied, so we can write E at infinity is actually equal to limit value when time goes to infinity. E of t is actually equal to s multiplying, or actually let's first write the limit when s goes to 0, s multiplying E of s. If we substitute the value of E of s from here in this equation, and if we multiply everything by s, we will actually obtain that E at infinity is the limit value when s goes to 0. What do we have here? We have s squared plus 3s plus 2, and in the numerator we have s squared plus 2s minus 3. Okay, so we simply need to evaluate this limit value. We can substitute s for 0 in both of these expressions, and we will obtain minus 3 divided by 2. And that's it. That's the final value, or better to say the steady state value of our control error.